This is the origin, Humanities Forum, so I wanted to start with the origin, the big one, the origin of all things, the origin of the entire universe. You still can't hear me? Oh, on this? Oh, okay, sorry, I could. Is that better? Okay. I kind of march around, so this is going to be tough. And there's some of you over here. So I was going to discuss the origin, as I said, of all things, really, literally all things. And not just things, but also all energy, and not just all energy, but actually of the universe itself. So when I discuss the universe and the origin of the universe, I think it's fair to ask, what is a universe? It's like a light show. That's for dramatic effect, and then the chorus comes in. And the universe is, of course, the matter and the energy in the universe. People are used to thinking about the universe as being the stars in the cosmos, the planets, not just the stars and the planets, but the galaxies, which are collections of hundreds of billions of stars. And then the collections of galaxies may be clusters. So we're used to thinking of that as a universe. What I want to impress upon you is that we should also be thinking about space-time itself, the actual space in which this matter and energy sit as part of the universe, a fundamental part of the universe. And so just so we can do a quick review of what space-time is, you're used to thinking about a north and south dimension, for instance. That's one dimension of space. And maybe an east and west dimension, giving a second dimension of space. So if I want to say where I am in Manhattan, I might give 3rd Avenue and 10th Street. That gives two coordinates, 2 dimensions. But I should also tell you where I am in the up and down, the 3rd dimension. Maybe I'm 5 stories up in a building. And that's really not enough to specify where an event is or where a person is in the universe, because I need one other dimension. And can anyone guess what that dimension is? Time, very good. I need to tell you when I'm going to be there. 5 p.m. on a given day. So the universe, we're used to thinking of having, you're having to specify 3 spatial dimensions and 1 time dimension. But for many years, the history, as far as we know it, of civilization, people thought of space-time as this rigid background against which the events of the universe unfolded. And it really wasn't until Einstein that we started to think differently about that. Einstein taught us that space-time is mutable. It can evolve, it can stretch, it can bend, it can curve. And what we'll discuss today is the question of whether or not it could actually have a beginning. So when we're talking about the universe in a picture like this, I'm imagining space-time itself as being, in some sense, the most fundamental aspect of the universe, and the matter and energy in it as another component. Now, every time I give these lectures, somebody asks me, but what's outside of the universe? So I'm showing you the wrong way of looking at the universe. What's wrong about this picture is we're standing outside looking down on this bubble as though we are independent of space-time, as though we can float outside of space and time and look down on space-time and say, what's outside of the universe? We cannot do it. It is not a sensible way to think about things. We are all bound to space and time. We are all bound to that aspect of the universe. We cannot step outside of it and look down into it. It makes no sense to ask what's outside of space-time. So if you imagine you're standing somewhere outside of space-time when you're saying, how far can I go outside of space-time? It's not a meaningful question. That's supposed to be a ruler. If I hold a ruler outside of the universe, it's measuring space, it's measuring length. So if I can do that, then that is also part of space-time. We might talk a little bit about extra dimensions, maybe if I get asked a question or if I feel like it later in the talk. Okay, so I want you to think instead about being inside the universe. Does everyone recognize this place? We are inside the universe at a very specific location. We're sitting on this very beautiful planet. We're hoping it's not the only one of its kind out there. And this planet is in a specific place in the cosmos. It's in a solar system. And obviously this is not drawn to scale. We've been displaced from the center, but I somehow made us much bigger than we should be. So this is a schematic of our solar system, at least a handful of planets, not all the planets in the solar system. So we live around a star. It turns out to be a rather ordinary star in a solar system, which is a collection of planets. And that solar system resides in a galaxy. There you are. you're in the spiral arms. I have this pointer. Is it working? So it's kind of hard for me to turn around with my mic. So it's interesting that the Milky Way galaxy, the galaxy in which we live, which has hundreds of billions of stars, has these beautiful spiral arms. And they're collections of gas and dust and stars. And between the arms are these kind of gaps. And I think I heard recently that we're floating a bit in the space here. I don't think I'd fully appreciated that before. In the center of the Milky Way galaxy is a black hole, something like 3 million times the mass of the sun. So we have an interesting galaxy that we live in. But that's not the whole story. Immanuel Kant once looked up into the sky and saw these smudges. There are some galaxies you can barely see like smudges in the sky with the naked eye if you're in a dark enough place. And he wondered if they were other island universes. And indeed, there are other galaxies out there. So where is our galaxy? I'm going to show a little piece of a movie. This is from the Sloan Digital Sky Survey. From the people at Cosmos. Oh, sorry, their name was supposed to show up here, at the University of Chicago. In this picture, in this movie, and it's not exactly an animation, it's made from actual data. The sun, we're receding away from the sun, and as we recede, we see thousands of other stars, millions of other stars, billions of other stars, until you get an image of the whole Milky Way galaxy. And as we move millions of light years away from the Milky Way galaxy, the distance that light could travel in millions of years, we begin to see other galaxies come into our field of view. So these other galaxies are also collections of hundreds of billions of stars. And they are millions of light years away from our own galaxy. And as you keep getting a wider and wider field of view to look at what the cosmos looks at, we see that there are thousands, millions, billions of other galaxies. As far as the eye can see, there are galaxies. And they begin to pile up on these filamentary web-like structures out in the cosmos. It's really quite spectacular. So again, this is data. This is built on data that's been taken by the Sloan Digital Sky Survey. So the universe is full of stuff. And there we are in the universe. And I wanted to convince you that while the universe is full of stuff, it's also the space-time that's somehow relevant. So we're going to ask the question, where did it all come from? We get to these huge scales where we see billions of galaxies across hundreds or even thousands of millions of light years, and on these huge web-like structures, and we have to ask the question, where did it all come from, and did the universe have an origin? And of course, as is expected, this story goes back to Einstein. Einstein believed, when he wrote down his general theory of relativity, that the universe was permanent. He believed this. And his general theory of relativity is written here. Now, they tell me never write an equation down. Are you stampeding for the exits? I write it down only because it's very beautiful, and to impress upon you, this is only one way of writing down Einstein's theory, but to impress upon you how simple it is. And it's not just notation. It's actually quite a simple relationship. And what this equation says is it says that matter, that's what this term means, things like the Earth, curve space, and that's what the left-hand side means. It tells you about the shape of space. It says that matter, like the Earth, actually causes curves in the fabric of three-dimensional space, and I should really say space-time. And objects like the moon, when they're orbiting around the Earth, what they're really doing is falling freely along these natural curves created in the space-time. It's absolutely a beautiful idea. I think as soon as you hear it, even if you don't quite grasp it, it rings somehow of significance. When Newton wrote down his theory of gravity, which was a mathematical expression defining how the apple would fall from a tree, it was incredibly correct in the sense that Kepler's orbits were predicted from it. It could predict the planetary orbits incredibly well. We had never seen a deviation from Newtonian gravity. But even Newton said there's something weird about that because the Earth is pulling on the apple, but it's not touching the apple. It's like action at a distance. Einstein thought that's as weird as mind-bending a spoon. Okay? He couldn't believe that the Earth, without touching the apple, was pulling on it. And he has this beautiful leap of intuition that what's happening is the Earth is curving space-time, and things are falling along those curves in space. And it takes care of a problem that Newton knew he couldn't solve in his own formulation. Now, when Einstein wrote down this theory of relativity, other scientists came along. Many people believe that Einstein discovered the Big Bang, and that's not exactly true. He discovered the theory which predicts the Big Bang. But other scientists came along and, studying this equation, said, imagine that I'm not talking about the Earth or the Sun, but I'm talking about matter spread on, maybe they didn't think about web-like filamentary structures, but they could have. Galaxies everywhere, matter spread everywhere throughout the cosmos, almost evenly, in a kind of average distribution of matter and stuff everywhere. What would happen to the universe? And that picture I showed you is kind of like that. It's as though there is structure everywhere in the cosmos. And what they realized is it predicted that the universe was expanding. What they predicted is that if I imagine this box represents some slice in space-time, and these yellow splotches are like galaxies, what they realized is it predicted that the whole box was stretching, getting bigger and bigger and bigger as a result, as a presence of those galaxies. It's as though the galaxies themselves are not moving. They're sort of sitting in some fixed location on the box, but the whole box is stretching around them. And then they thought, if you run the movie backwards, then, you want me to answer that? Is that someone's phone? Somebody calling to correct me or something? So if you run the movie backwards, the box gets smaller and smaller and smaller. So you imagine going backwards in time, what must the cosmos have looked like? Well, eventually it must have been so small, if I run it backwards, and it was expanding this whole time, then the whole universe must have been crunched down to a tiny area, smaller than a galaxy. And if you keep running the universe backwards, smaller than a thimble, than a speck of dust, than a dot, than any extent at all. It becomes essentially crunched down to nothing. What happened before that? They don't know. They looked at Einstein's theory and they said, before that, there was nothing. No space, no time. This is something we'll come back to, whether or not this is a naive notion, because this whole idea of origins is really rooted in exactly this question. What happened at that moment? Was there really nothing? But when they ran the movie forward, there was the Big Bang. And the modern notion of the Big Bang was born. You run the movie forward, and the idea is maybe out of nothing, the entire cosmos is created. There's a Big Bang, an explosion. Not an explosion into space, as though space existed and sat out there and matter merely rushed out into that space. But it's the creation of the space itself, like a sheet of rubber on which the matter is distributed and the matter just goes along for the ride, stretched out as that whole space stretches. If you ask, where was the center of the explosion of the universe? The answer is that the center was everywhere. We are in the center. The center was everywhere because the center was once crunched down to a dot and stretched. So this is a very profound prediction, and Einstein absolutely resisted it. He refused to believe that the universe was expanding and that it had a beginning. I think this is very interesting. I'll return to this again, this discussion, but he called it his greatest blunder because he could have predicted himself the origin of the universe, but he resisted. I should say, well, I said earlier, just to correct something I said, that there was no known deviation from Newtonian gravity. That's not quite right. There was one tiny deviation having to do with the orbit of Mercury. The planet Mercury doesn't execute a perfect ellipse. It sort of precesses slightly. The ellipse swings around as it orbits. It's a tiny, tiny correction, something very, very tiny over centuries. And Einstein's theory it was the first success of Einstein's theory that it was able to match that prediction. And when Einstein calculated that and realized he could match that prediction, he said he had heart palpitations, which I think is really cute. For days, he said, for days. So in the 1920s, Edwin Hubble comes along, the great astronomer after whom the satellite is named, and he begins to look at all the galaxies that he can see out there. Not the ones very close to us, because some of those are actually falling into us and we're falling towards others because there's some local stuff going on. But if you look at all the galaxies as far out as you can see, further away, they all appear to be moving away from us. In every direction, the galaxies are moving away from us. And the further away they are, the faster they're moving. And it might sound, just hearing that at first blush, that means we're at the center of the explosion. How many people think that's likely? Yeah. We're not at the center of the solar system. We're not at the center of the galaxy, and we were not at the center of the explosion. If you go to any other galaxy in the universe and ask, what does it look like? They would say, it looks like every other galaxy is moving away from me. And the further away they are, the faster away they're moving. It's a very unusual picture. And what it symbolizes is exactly this description. Do I have a picture of it here? Sorry, let me just see. No. Okay. Is this description of space stretching between the galaxies. When the universe is created, the space and time is created, and it stretches. It stretches from the energy of that event, and it begins to grow incredibly quickly. We'll talk about some of these early epochs in the universe's history. And as it grows, it's as though all the stuff in it is kind of sitting there, more or less. So when Hubble came back with these observations in the 1920s, Einstein immediately capitulated. He knew immediately that he had been wrong. And it's very interesting to me that somebody who's willing to give up the absolute nature of space and time, the permanence of the universe, still threatens him. And a lot of times people will say things to me like, do you believe? And I tell them, it doesn't matter what I believe. It didn't even matter what Einstein believed. And that's a significant aspect to science, that even our discoveries surprise us. So what do we know about the Big Bang? Well, what has been confirmed? So Hubble confirmed that the universe is indeed expanding in such a way that confirms this very unusual prediction. The next prediction was that there should be some light left over from the Big Bang. The Big Bang was this incredibly hot, high-energy event, and it's cooled since it happened. It's cooled over the epoch of cosmological history, and so there should be some remnant of this light, some echo of this light. And sure enough, that's been observed. And although I have nothing against New Jersey, I somehow think it's funny that it was observed in New Jersey for the first time. I don't know. Do you guys here you are looking. They're looking out at the sky. What happened is Penzias and Wilson were building a microwave dish, a huge dish, for some technological reason for Bell Labs. I don't remember the exact reason, but they could not get rid of this very faint signal. It was everywhere. They pointed it at New York City. They pointed it away from New York City. They pointed it towards the galaxy, away from the galaxy. Wherever they pointed this dish, there was this signal. It was extremely persistent, and it was the same in every direction around the sky. And sure enough, they had observed essentially the Big Bang, the radiation left over from the Big Bang, the cool echo of that incredible event. When they wrote their paper, I think they said something very conservative, like this might have cosmological significance. They were terrified of being the lunatics who said they had observed the background radiation from the Big Bang. They did get the Nobel Prize for their work, although I always kind of plug the theorists because I thought Gamow and Beta and who else? Maybe Peebles even should have gotten the Nobel Prize for that. See, now I distracted myself with some politics. So sure enough, now we know Nobel Prizes are given out all the time. 2006, Smoot and Mather got the Nobel Prize for remeasuring this radiation, but to great precision with incredible detail. So this is something that's very solid in the canon of cosmological evidence for the Big Bang. So let's review the picture. What happens after the universe is created? Okay, there's space-time. That's supposed to symbolize space-time. And there's something else going on. This is the part we don't understand that well. And I'm talking about a minute fraction of a second after the universe is created. We're not exactly sure what preceded. It might have been cold. It might have been hot. We're not really sure. It's very likely that it was a quantum event. And quantum theory or quantum mechanics refers to a description of the laws of physics on the smallest scales, if you were to probe the scales of atoms and subatomic particles, and also the highest energies. When things look like they come in individual bundles, everything is individual. You look at your outer skin and you think it looks solid, but of course you're mostly empty space. It's just that the way light reflects off your skin makes it look solid. Really, if you could probe this at higher energies, as you do with things like X-rays, you discover basically it's mostly empty space with just little bits of individual bundles of stuff. And when you get to the quantum world, it looks lumpy like this. Everything broken up into individual lumps and pieces. And in this picture, those individual lumps and pieces refer also to space-time itself, it's believed, although we don't exactly know how to formulate that. That literally, there'd be little chunks of space-time. And it wouldn't be smooth, the way we think of it as being smooth. It's also believed that it was probably a hot event. So let's just go with the scenario, which was the original description, of imagining that the early universe, when it began, was extremely hot when it began. And in this case, hot means 10 million billion times hotter than the sun. That's really hot. Technically, that's how we refer to it. And at these temperatures far greater than anything we can ever fantasize about reaching, even in the greatest accelerator experiments, billions and billions of times higher energy than that. At those scales, all forms of matter and energy, as I said, including space-time, was not only in these little quantum bundles, but might have been unified. And by that I mean they might all have looked exactly the same. If I think of these as little quantum bundles of energy, matter, and space-time, I couldn't tell which one was which. It would be impossible to distinguish at these energies whether I was talking about matter, energy, or space-time. And this idea of unifying all of the laws of physics, matter, energy, and space-time, into one simple description is the hope, the ambition of theoretical physics since Einstein. And it was also Einstein's hope. We're not quite there yet, but we're getting there. Another theory that's been promoted that's very important is one by Alan Guth from MIT, who suggested that this long after the Big Bang, that's a 1 with 35 zeros preceding it, a very, 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 very tiny fraction, tiny fraction of a second after the Big Bang, that this quantum energy of space-time itself drove the universe to expand, not just from the explosion itself, but exponentially. Actually, the expansion got faster. Maybe exponentially was a strange way to put it. It's just, I'm so used to saying that. I should have said that the expansion accelerated, because that's really the key thing. That it got faster and faster and faster, and as it was doing this, it seemed to stretch out all of these lumps and bumps and dilute all of the matter. Imagine you have a lot of particles in one region of space, but that space grows so intensely, it dilutes the matter so that it looks like there's hardly anything there anymore, because you've made the space so big. You know, you have a handful of sand, it looks like a lot of sand. You throw it into a basketball court, it doesn't look like a lot of sand anymore. So it dilutes all of the matter and energy so much that the universe appears smooth, cold, and essentially empty of particles. It just looks smooth, cold, and empty. But there is still this energy trapped. And this energy is trapped in some sense in space-time itself. You imagine stretching the membrane of a balloon, and it has an energy itself. It's not exactly right, but it'll work for our purposes. And there's this energy trapped in space-time itself. And the idea that, well, Guth's ingenious idea was that this could happen, making the universe large, because even though the universe came out expanding, it was very hard to understand how it got so big, and also made it smooth. And one of the very peculiar things about this radiation left over from the Big Bang is that it's smooth. It's incredibly smooth. It looks the same if you look in that direction as if you look 180 degrees opposite. And light that's been traveling billions of years to get to you from across the cosmos in two totally different directions seems to be exactly the same temperature. And this is very surprising. And this was one of the very important explanations that inflation offered. It made an explanation for why the universe was so smooth on such huge scales. And inflation is not completely verified as a theory, but these experiments on the radiation left over from the Big Bang match very, very well the predictions of inflation. So there's reason to be optimistic about inflation's success, that its survival as a prediction for the early universe. But this is still our kind of cloudy era. Then all of that energy that's sort of trapped in the space-time gets released. And in some ways you can think of this as energy in water as it heats up right before it bubbles, right before it sort of boils over. It gets released, and the energy that gets released becomes all of the matter in the universe. So the universe, which was cold and empty, all of that trapped energy becomes released, and it becomes hot and full of stuff again, hot and full of particles. And we have what's known as a hot primordial soup. I had a professor friend at the University of Chicago when I was a graduate student who Rocky called, he would make these Campbell's soup cans with, instead of saying chicken soup, it said primordial soup. And it said like heat to 10 million billion degrees. And the ingredients were things like quarks and leptons. Anyway, he's funny. Now the universe expands. After inflation, after it's released all this energy, it expands just from the presence of stuff in it, the way people predicted before inflation, but right after Einstein. But it expands much more slowly, and it begins to cool. And as it cools, now we're at about 3 minutes after the Big Bang. Our predictions are really well confirmed by observation. So the part that I said is foggy, that we're muscling through, but we still have some important information indicating it's right, is from a minute fraction of a second after the Big Bang. But by 3 minutes, we got the story down. So that's pretty impressive. 3 minutes after the Big Bang, we got the story down. This picture is supposed to indicate that atoms began to form, and that this idea that everything was so unified, I couldn't tell a chunk of space-time from an electron or a particle. Well, it's gotten cool enough that now I clearly know the difference. Space-time looks like this smooth, stretching background, and atoms look like these quantized lumps, and I can begin to see them forming out of this hot soup. And in this early epoch, by the vast majority of stuff you make is hydrogen, which is a very, very simple element, the simplest element in the periodic table. And you might make some deuterium and maybe a splattering of other stuff. And that prediction is very well confirmed. When we look out at stars and galaxies that we think are made up of primordial stuff, the components match exactly what's predicted to incredible accuracy. This was really one of the great and early successes of cosmology before this field was still taken very seriously. And so this is one of those observations that however you try to imagine the early universe, you had better get this right, because we know that this is how things began. I'm just going to digress for a second to make what I think is kind of an interesting point. If people haven't heard it before, it's one of those classic things that get said a lot if you ever take an astronomy class, but I don't know, maybe people haven't taken an astronomy class. So I'll tell you this, that in the early universe, I said you mostly make this very simple element, hydrogen. And of course, what's the most fundamental basis for life? It's not hydrogen, right? It's carbon. Carbon is not made in the early universe. If the early universe happened, but there wasn't something going on afterwards, no carbon, no oxygen, no water, okay? No rock to form the earth, no water to fill the oceans, no atmospheres, and certainly no life, no DNA. And all of that, all of the material, the atoms that go into making this very important stuff for the emergence of life is synthesized in the cores of stars. So after the Big Bang, well, maybe I should get to the stars. Stars begin to form. I'll show you a little movie of that in a second. And galaxies form. And in these galaxies and in these stars, in the cores of the stars, they're basically nuclear reactors, fusing simple things like hydrogen to heavier things. And it continues to fuse these simpler things into heavier and heavier things, making things like carbon and oxygen and nitrogen and sulfur and all kinds of things. And then the star runs out of thermonuclear fuel. And in many instances, it catastrophically collapses under its own weight, having lost the fuel that was kind of keeping it up and keeping it bright. And it collapses, and under the weight of that collapse, it bounces back out again in a supernova explosion. And many people have heard of supernova explosions. The importance of supernova explosions to life is that they expel all of that stuff back out into the universe. And so it can only be in a second generation of stars and galaxy, well, maybe not entire galaxies, but of stars, where you can form a planet that's able to sustain life. So I think it's a very interesting story about how we emerge as progeny of a cosmos with very specific cycles. Let's see, did I put a time on this? A few 100,000 years after the Big Bang, This is supposed to indicate the radiation left over from the Big Bang. It begins to cool freely, which means it's no longer scattering off of a lot of stuff out there. It's no longer interacting a lot. It's just this sort of light left over, but it's trapped in space-time itself. And so it just sort of sits there, this bath of light, as the universe expands. And in it, there are these tiny, tiny hot spots and cold spots. And I say they're tiny because I told you that the impressive thing about this radiation was that it was the same everywhere. These spots are smaller than 1 part in 100,000. And so it's very, very small. If you went to a civilization on the other side of the planet and you discovered that they spoke the same language to 1 word in 100,000 as a civilization, very far away, you would believe that they once had been together, because it just wouldn't make any sense otherwise. And it's some similar thinking that brought Alan Guth to think that the universe was once very small, closer together, and just grew exponentially, that it inflated. And this is the fossil record that we use all the time to understand these very early epochs in the universe's history. So all of this is very solid, observationally confirmed. This picture is, again, from the Center for Cosmological Physics at the University of Chicago. Actually, hold on, I'm going to have to run it again because it's already over. Okay, let's start over. So here it is, and this represents a distribution of matter in the universe with maybe some tiny bumps, 1 part in 100,000, the kind of scale that you see in the radiation left over from the Big Bang. Tiny bumps in a universe full of matter and energy, and those lumps are just enough that stuff starts to fall into maybe colder regions or get pushed out of hotter regions. That's maybe one way of thinking about it. Or you could think probably better of the space-time as having been curved more deeply when there's slight fluctuations, and that draws matter into a well, and matter begins to clump into a well. And what happens, as this movie shows, is structure begins to form. So this is a numerical simulation. This is not data. This is run on a code using the laws of physics as we understand them to, I don't know why it restarts so fast. Let's try it again. To simulate how galaxies would form on these web-like structures that we see in the actual data. And so it's a beautiful confirmation of what we see, again, matching our ideas of mathematical ideas to what we actually observe. And this happens over the course of the universe's history. And here's what some of these galaxies look like up closer. This is from the Hubble Deep Field. Really spectacular images. Some of these are foreground stars. It's very bright thing shining. But these are entire galaxies. And it's really spectacular. They just go wherever you look, galaxies on all angles, all over the place. It's really some amazing stuff. So from the first 3 minutes until today, and when's today? It's 13.8 roughly billion years later, after the Big Bang, we have all of this evidence that confirms our cosmic history. We know a lot, but we don't know everything. So you have to think about where cosmology went. The idea that there was an origin to the universe was absurd to Einstein, absolutely absurd. Then it becomes something that we now take for granted. We all grow up talking about the Big Bang, the idea that the universe had an origin. 14 billion years ago, roughly, the universe was created. And I'll get back to that question. But in the meantime, I just want to tell you what we do know. So it feels like we know so much, but we decidedly do not know everything. So what don't we know? And this is where cosmology has become a very precision science, but it's revealed some really spectacular and surprising things. Let me just go back to that story. But what Einstein did, he was so mortified that he actually altered his equation. And again, you don't really have to know what this is, but I think it's kind of pretty. So. And he added something to his otherwise perfect theory. Here's his perfect theory. It does beautifully. It matches Mercury. It's wonderful. But he says he can't live with the idea that the universe is expanding and that it had a Big Bang. So he adds this term. It's called the cosmological constant. And he adds it in a hope that it will make the mathematical prediction predict a universe that doesn't expand, that is permanent, that's static. And it actually works, but it doesn't work well. It's unstable, meaning it actually doesn't work at all. If you knock it, it's like, you're balancing a table on one leg. For a second, it'll sit there, and then it falls apart. And so he realized that actually what this thing really does, this term he added, is it causes the universe not just to expand, but to accelerate, to get faster and faster and faster. And I said that was the hallmark of inflation. And in fact, this is exactly what Alan Guth used to drive an accelerated expansion. He said, imagine there was a cosmological constant like Einstein once talked about. That would actually drive the universe to accelerate, not just expand. The guy can't make a mistake, you know? So recently, to make things even worse, there's evidence that not only might there have been an era of early universe inflation, but also the universe seems to be accelerating today. And we don't know how that happens. I'd like to say, instead of calling it, I just mentioned this historically, but what we really call it today is dark energy. So what we really say today is that when we look out in the universe, it looks as though there's some energy of space-time itself, of empty space, as though that has some energy associated with it, maybe some quantum energy. And we call that the dark energy. And we deduce it's there by looking, essentially, measuring the curvature of space-time in various ways, or measuring the expansion rate of the universe in various ways. And it seems to be that there's this kind of energy. We don't know what it is. We can't see it. It's called dark energy because we can't see it. Literally, it doesn't reflect light. That's all it means. So it's called dark. It also appears that there's lumps. This is supposed to indicate lumps of matter. There's lumps of matter out there that we don't know what it is. It's called dark matter because we can't see it and we don't know what it is. It's fundamentally different than anything, you know, that wood is made of, than we're made of, than the stars that we can see are made of. It's fundamentally different than anything else we've ever seen. And the rest of the universe, the stuff that we do see, all of this stuff, well, that's ordinary matter and energy. We can see it and we know what it is. But it turns out that it's less than 5% of what's out there. At least that's what our very detailed observations are telling us. 95% of the matter in space-time is of a form that we can't identify. Now that's actually exciting for people like me, because that's how we stay in business. And so what do we know? We know the universe is expanding. We know that the early universe was hot and dense. It looks like there might be something like dark energy and there might be something like dark matter. I'm not going to put it on the same footing as the expansion of the universe or the radiation left over from the Big Bang, because we're just grappling in the dark. There's strong indications it's out there, but until we hone in on what it is, it just becomes this mystery. And so this is the focus, not just of cosmology, but to a large extent of theoretical physics as a whole, because it indicates that there must be something beyond what we know in ordinary physics. And by ordinary physics, I mean extraordinary things like particle physics of subatomic particles, the way gravity behaves according to Einstein's theory, all of the things we think we know. This says that there must be something beyond even that. And this is not that unexpected if you believe this idea of unification, that back in the early moment of the universe, everything was unified, everything was once quantum and put together. You would expect that we don't know the whole picture, and you would expect that there would be other things. I think the big surprise is that it dominates the energy density of the universe. I think that's the big surprise. I'm slightly moving here. I want to not take too long with this, because this is kind of an exhausting subject now, and I want to leave a lot of time for questions. So I'm only going to do a little bit of this, and it was mentioned in the introduction. One of the things we also don't know about, I wanted to bring this all back to the early universe. This question of the dark energy, the dark matter, is ultimately, to my mind, a question about the early universe, because it's about this moment of unification, about what really went on in that era that I can't quite describe. And something else that happens right after the universe is created has to do with its shape and size. And one of the questions that I've worked on is, when it was born, was the universe instantly, infinitely big? So does that make any sense? Einstein said only two things are infinite, the universe and human stupidity, and then he added, and I'm not so sure about the universe. And he wasn't. He knew that it was possible to imagine a finite universe. And since his time, the mathematicians have gotten a lot better at explaining to us how to think about finite three-dimensional space-times, and so we were able to do things that maybe they hadn't quite thought of in Einstein's day. I'll just tell you a little bit about motivating this. So the question is ultimately, is the universe infinite? And if it is infinite, can you imagine an infinite number of galaxies out there? And if there are an infinite, literally infinite number of galaxies, are there an infinite number of planets in these galaxies? And if so, some of them must be infinitesimally similar to the Earth. And somewhere else there's a place called UPenn in the cosmos, and they're having a conversation, but maybe they figured it all out. I don't know. Maybe they have the answers. And it just seems an absurdity. So we try to imagine, what's it really like to live in a finite universe? What would that mean? And I say that this is similar to imagining that the Earth is finite. And so let's just try that for a little while. This is a picture not of Spain, and not of Columbus. My geography's bad, but it's not that bad. You remember, European explorers, or so the lore goes, feared that Columbus would simply sail off the edge of the Earth because they believed it just had an edge. And it might seem that the other alternative is that it's infinite, but of course we know that the real solution is much more beautiful than that. The Earth is finite and edgeless and connected in this nice way. So that if you're Columbus and you leave the coast of whatever continent it is and you travel in a straight line, you do not turn left, you do not turn right, you do not turn around, you will eventually just come right back to where you started. And it's something like this that we're imagining for the whole universe. Not that it has some ugly edge and you simply sail off of space-time. Not that it's infinite, but that if you were a space explorer and you were to leave the Earth, let's say, for a distant galaxy in a distant solar system, and you were to travel in a straight line so that maybe you saw the Earth recede behind you as you traveled, and another planet approach you as you got to this other galaxy. I mean, maybe it's taken you 10 million years to get there. It's a long time, but you were traveling at the speed of light. So it takes you 10 million years to get there, and you get down on the planet. How would you even know it was the Earth after 10 million years? Anyone seen Planet of the Apes? The Statue of Liberty is buried in the sand. That's how you know. And you get out and you realize this is the Earth. So you traveled in a straight line, you never turned left, you never turned right, and somehow you made a round trip around the universe. And it's this idea of the universe being connected, finite, and edgeless that we were pursuing when we were asking about whether or not the universe is infinite. I'm going to apologize because I don't like to do this, but I'm going to skip some of these frames because I don't want to go too long. And so the question becomes, as we look, we can't do this experiment. We can't leave our planet to go beyond the moon, let alone, well, let's not talk about Mars, let alone going to another galaxy. But we can sit back and say, even the light traveling from another galaxy, if it traveled far enough, could go on this round trip around the cosmos and come back to us. That means that even the light from our galaxy, the Milky Way, could be emitted 1 million years ago, 10 million years ago, 100 million years ago, travel all the way around the universe and come back to us. So that when we look out into space and we think we're looking at other galaxies, the question is it possible that some of those galaxies are really reflections of our own? That's pretty weird, Now, the data, I would say, I would find it very surprising if that were possible, because it would be about naturalness. Is it natural for the universe to be big, but just small enough that we could see ourselves on the horizon? Why shouldn't it be so big that in 14 billion years, not even light has been able to make the circuit? So that's a question. Is it just so big that not even light, that the light from our Milky Way is still trying to make that round trip, and it'll be trying for way longer than the age of the universe? So these questions of naturalness are another issue, but it's not something we can resolve yet. And so this question about whether or not the universe is finite in space also connects with a question about its age. Is it finite in time? And we said it's 14 billion years old. We said there was a Big Bang, and it's 14 billion years old, and that was the origin of the universe. But now we look at things a little more differently, and we say this idea that there was nothing, and then suddenly there was something, and 14 billion years later all of this stuff happened, seems naive. And some of the ideas that get floated around are that really what happened was maybe a tiny patch of an eternally existing universe, space-time, blew out, you kind of imagine, this is very schematic, into a Big Bang, had a Big Bang event, if you like, inflated, became a bubble, became a universe, and all of the inhabitants of that cosmos, maybe 14 billion years later, look back and are blinded by this Big Bang event. And unknowingly, they're actually connected, we're actually connected, conceivably, to a larger space-time. A space-time in which there have been other plumes and other bubbles, in which there have been other things like a Big Bang. Maybe some have not been so successful. Maybe those bubbles collapsed on themselves. Maybe in those bubbles the laws of physics are slightly different, and carbon never formed, and oxygen never formed. And maybe there's an infinite number of these bubbles, like an infinite ginger root. This idea that there is a megaverse, of which we are just one small plume, is not something that can be totally dismissed. It sounds fantastical, but you have to remember how fantastical it sounded that the universe had a beginning. Now, the megaverse, in some sense, has no origin. So I wanted to kind of shake things up in the first lecture and talk about the origin of all things, and then maybe suggest that it has no origin at all. So just to conclude, we know that our patch of the cosmos had an origin in the Big Bang. That is very solid in our observations. But what we don't know is if it's connected to some vaster space, if there's possibly an entire universe, so to speak, in this megaverse where there are galaxies and planets and possibly even life. And the question about the origin becomes a question of not just the origin of our plume, but whether or not the actual whole space-time is eternal. Thank you.